so you're not going to be released early, sorry. But anyway, you can all hear me okay? Okay, good, thanks. So this is the last talk of the day, and I'd like to echo all the thanks that the other speakers made. To always admire people who put so much work into a voluntary kind of initiative, and appreciate it all, so thanks. So this talk, I'm a bit of an R evangelizer, so I wanted to do something that I thought was useful. And it took me quite a long time in my R career before I discovered the profiler and how good it is. So I thought I'd like to share that, and perhaps all of you already know it, but I don't know. So if you tell me that you already use the profiler and you're happy with it, we can break early with Andrew's permission. But if not, then I'll go through my talk. So let's see. Okay. All right, so hopefully this will work. Oh, gosh. Okay, cool. So I call it R's best kept secret just because, like I said, it took me a long time before I really got there, and it's just a really amazing tool. It works really well. So just a little bit first about our company. So we're a software development and consulting company. We specialize in optimization, sort of OR type problems, mainly in supply chain optimization. We've got about 60 people in the company, but we do a lot of work on R projects, both for internal use and for customer facing in production. And so we really need and where it makes sense, we use Shiny and R to deploy really full and complex systems. So I've heard a few people saying how it's difficult to create sort of big users, big systems being used by many people with R and Shiny, and that is true to some extent. But we're kind of weighing up the benefit. And because obviously it's really productive, you get things out very quickly. You can change things. It's really a very highly efficient way of producing systems. But sometimes we also have performance problems, and the profiler is a really big help in solving these. So, just to give you a little outline of where I'm going with this. First of all, I'll just quickly discuss what is profiling for people who haven't come across it yet. And then overview of why profile. We'll just talk about why we will need to profile. Then I'll explain a little bit about how the R interpreter works. Because I think for people who've got a CS background, which is probably nobody here, right? I don't know. So anyway, if you've got a computer science background, you know exactly how an interpreter works. You've written one. Everything I'm saying now is completely basic. But most people who come into R are not coming from a CS kind of world. And so I'm going to spend a little bit of time really talking about how the interpreter works. And then I'll also spend a few minutes, or maybe one, on using profiling versus benchmarking and the actual benefits of each. Then I'll talk about the R profiler a little bit. And then the best part of the talk is the demos, I suppose. So if everyone can just stay awake till then, that's fine. And then finally, I'll just give you an example of really why I think this is such a great tool. Where we really used it. It saved us a lot of money and a lot of time, and it was really useful. All right, so just what is profiling? In general, it's just a set of methods for understanding what's taking time in running code. You've written a big piece of code. It's running for too long, normally, and now you need to understand why. So there are a few methods of attack on that question of why is this code taking too long to run. One of them is using profiling, which is really the ability to dynamically understand what the bottlenecks are in your code by automatic analysis of what's happening. And that's what makes it so powerful. So, okay, so I guess if you're not convinced, or if you've never come across a performance problem, maybe I need to convince you. So before publishing code, whether it's production code or a package, we should try and make sure it doesn't waste resources. We should try and make sure that it's as efficient as possible, both in terms of memory and execution time. So if you look at the R recommendations, you should really profile any package before you submit it, and it just makes general hygienic sense to do that with all your code. And it's often easy to get big improvements without big restructures. So you don't have to be afraid of doing this, thinking, oh dear, if I find problems, then I'm going to have to rewrite my whole package. There's really often little things that you can do that have big impact. The other thing is that point number 3 is, like I said, I think R is, I hope everyone agrees that R is more than a prototyping language now. We need to build, or lots of us are building, large multi-user systems with R, and so it has to be efficient, both in terms of the cost of the computing resource and in terms of the response that we're giving our users. And this is especially hard with Shiny. I mean, I don't know how many of you are Shiny developers. Maybe this will be interesting to see. Just a couple. I'm kind of surprised. I thought it would be more than half. Anyway, so if you are a Shiny developer, you'll know that it can be really tricky to understand when things execute and how often. I'm sure everyone who spent more than a few days building a Shiny app would get to the point where they say, why the hell did that run? Or, you know, what's going on here? So it's not always clear when the Shiny reactive expressions will be executed or how often. And then the profiling really helps with that as well. So just to compare it to benchmarking, so I think one of the first things that people do when they're trying to speed up their code is put in all kinds of logging statements. So you log everywhere, and then you have to delve through all the logs to kind of find what takes long and so on. So, I mean, that's a useful approach, but first of all, you have to have an idea where the problem is, and then you must work through the logs to identify the problem. So, you know, I'm old enough to remember when this was our only approach, so it's still sort of okay, but that's, you know, it's not the best anymore. The other approach is to use a tool like Micro Benchmark. I don't know how many of you have used it, but it's a really great little package for getting an idea of how long pieces of code take to run. But it's not really useful at all to, so it's good, for example, like what's the best way to sum columns of a huge matrix? That seems to be an example a lot of people look at. But it's not much good for identifying problems in big systems. So, okay, so here's that little thing about the R interpreter. So, I don't know if this picture is too obvious for everyone, but your R program consists of your program plus a usually huge set of libraries. That's taken by the R interpreter, which just has a read-execute loop. So that read-execute loop reads the next line of code, executes it, and what does it mean to execute? It means either change some memory in your variables, or call a new function which adds a new function to the call stack. So it's that call stack that's the key thing that we're going to be looking at. So, for example, here I've got a little example of a factorial function on the left. If I call that factorial function with the argument 4, you see when it gets down to 0, then it just calls the browser. In the browser, I call where, and it shows me that I've got 4 function calls on the call stack. So as we build bigger and bigger systems, this function calls that function calls that function, and as they're calling each other, your call stack is building up. So during execution, the call stack keeps a history of all functions currently running and waiting for their called functions to complete. Note also that the variable memory is dynamically controlled by the interpreter. So the amount of memory being used goes up and down as you create and release variables. All right. So let me just try and explain to you now how the R profiler works. So this is a little metaphor that I came up with. I hope it's useful to you. Just think you're on a train. So this train is running inside 2 big walls. But every 100 meters, there's a little gap in the wall, and you can see out. So mostly the train's charging along, you don't see anything, but every 100 meters you get to look out through that little gap. So you won't see everything. You won't see every building. If there was a giraffe there, you might miss it. But you'll be able to tell, are you in town or country? Like, what kind of landscape are you looking at? Thank you. So this is exactly how the R interpreter works, that every 20 milliseconds, it pauses and takes a dump of the current state of that stack. So you might miss a whole lot of things. Remember, 20 milliseconds is eons in computer time. Well, not really, but it's a lot of time. And so, but still, you can get a very clear idea. Oh, that was, I did a little animation there for you of my train. There he goes. It takes 20 seconds. Anyway, so the train's chugging along. As it gets to each thing, it's going to take a little picture of the state. Okay? So how does the profiler work? The first thing to understand is that it's baked into the R interpreter. So the R interpreter has this capability, if you switch the profiler on, to pause itself every 20 milliseconds and then dump a copy of the current call stack and memory usage into a file. Once the execution finishes, the profiler output can be examined. And this is hugely facilitated by a fairly new package called ProfVis, which stands for Profiler Visualization. And that's a brilliant tool by Winston Chang, who's one of the lead developers at RStudio. And if he was here, he would give a much better talk than me. But if you want to see his talk, it's available. But I think it's just, so that's cool. So the first example I want to show you now is using this. So I've taken an example just from linear algebra. It seems like the screen has trouble adjusting when I change from the slideshow. Okay, so I'm not going to change back into the slideshow just so that we don't have to wait. Okay, so here's the first example. So you see I've got these three lines, pretty simple lines. I create a matrix, 1,000 by 1,000 matrix. Then I just do the matrix multiplication with itself, and then Z is the inverse of the matrix. So all you have to do is here, you go profile, and then say profile selected lines. And then it shows you over here two things. So for each line, it shows you the memory that's used and the time that line took to run. And down here, it has this thing called a flame graph. So why I've started so simple is this flame graph gets very confusing if you look at it on a more complex example. So you can see this first one, if you hover over it, it just says that was a call to matrix, and it took 40 milliseconds. Above that, it says there's RUnif, which also took 40. So basically, this matrix, this line, matrix called RUnif, and RUnif took all of the 40 milliseconds because that little bar there is over the whole thing. If you have a look at, so that's interesting because that tells you that the matrix function itself took almost no time. If you look at this one, this was the matrix multiplication. Now you see there's a blank thing there, a blank area. What that tells you is that what this called is unknown. So the profiler, if it goes into C code, it's sort of, you don't see anything, it's dark. If you look here at solve, so the solve took 920 milliseconds, and there the source was unavailable to actually do the solve. Okay, so that's the first example. That's the simple one. So this first one took 40 milliseconds, then it ran for 650 milliseconds, and it ran for 920 milliseconds. The second example, this is one from Winston Chang. So I think this one's quite illuminating in terms of it teaches us something about the R interpreter as well. So let's just look at this piece of code. So this piece of code starts off by creating a data frame with one column with 50,000, 5E4 is 50,000, right? Random values. Then it takes the cumulative sum, it just sets data $sum to data $value 1. Then it runs from 2 to the number of rows and adds into data sum the previous sum plus the new value. So that's just calculating a cumulative sum. I hope you all know there is a function called cumSum in R that would do this very quickly. But if you don't, then you might do it like this. So then you see this has also got in front of it a call to profviz. So profviz is just the name of the profile visualizer. So if I run this, taking quite a while, but don't worry, it's supposed to. Okay, cool. So now you get this more complicated kind of flame graph. And you can see this took 9. First of all, this used a lot of memory. Isn't that amazing? That's 224. No, sorry. 20. Is that? Yeah. So that's like 22,417 megabytes. That's a lot, hey? So what's happening here, and I'm sure for all of you who've got your R senses tingling when you see this, I hope, that there's something very bad about it. There's a few things that are bad about it, but when you run it, you see it also took almost 10 seconds. The yellow bars here mean that we know which line this came from. We've got the source code. The white bars, we don't have the source code. But look how interesting this is, that most of these have got the little dollar. So what this is telling us is that this dollar access is really slow. And you might be surprised by that, because if you've come from another programming language, accessing into a data structure costs almost nothing, or it can actually cost nothing if the compiler is correct. So this is something that's kind of interesting to understand, is how much of this time is spent just on this accessing. So the next example, what we do is we, instead of accessing this variable every time, we just make a little function called csum, then call it with data $value, and then here inside we're actually just accessing a vector, not a vector inside a data frame. So if we run this one, oops, so that was really quick, hey? That just took 40 milliseconds. And look how much less memory. It's still got a problem, which I'm sure some of you are realizing. But so here we called csum, and then it did some startup. So this is really just all startup stuff for the function. Then it goes into this loop where it spent 20 milliseconds. So you can see the total call to csum was 40. Half of that was on startup, and the other half was on the actual loop. So there's just 2 more minutes. That's fine. Thanks. I've just got one more example. And then, so then this last one. So the other thing that maybe those of you who kind of seasoned R programmers would be worried about, that you see here we say sum equals x1. So it's just a thing of length 1, and then each time we keep extending it as we're adding another element to that sum vector. So you could have started off by rather pre-allocating the sum vector, creating a big enough vector to store all of the results, and then you can do this. And then run it again. And you see now it's gone down to 10 milliseconds, of which was all really just in the overhead. The actual calculation took no time at all. So that that first example was bad, but it's not so bad that none of us would have written code like that, right? And that took 10 seconds. A little bit of optimization gets it down to almost no time at all. And you could see how the profiler really led us down that road to be able to do that. So, just final slide then. So this is the final slide. So how did this profiler really save us? So a couple of years ago, we started building quite a big kind of project in Shiny. And it worked fine for up to about 4 users. And then it sort of, with more than that, it started really slowing down and reacting badly. So we naively thought at the time, well, this is just Shiny. It's not good enough. We better go on to some more robust, enterprise-oriented kind of development environment. We spent, but still, we put the whole system through ProfViz, and really within half an hour we were able to very quickly find what the problem was. So the problem was that in some big loop somewhere there was a big load of data which should have been ahead of the loop rather than being inside the loop. And that's another kind of mistake that we've all made, I'm sure, where you just sort of put the load in the wrong place and then it just keeps on re-happening. We moved that and instantly the thing became usable for about 20 users, and that was adequate for our use case. So anyway, so I just wanted to share that with everybody because I think it's a really valuable tool to know about. And I also think that this is, you know, personally I feel that there are a lot of use cases where you can build systems for production, not all obviously, but I think that set of use cases is growing all the time. So thanks a lot.
Thank you. Any questions?
You got a question? Yeah.
Thank you so much. I actually so recently started using this, and actually one function that I was working on on average took about 5,500 seconds to run, and I got it down to 5 seconds with ProfViz.
Thanks.
And the one thing that I did find a bit irritating is if you're working on old-ish statistical code, it's usually a couple thousand lines of code that you need to run through, and you need to wrap that code in ProfViz. So I don't know if you found a way to have ProfViz actually look recursively almost. So let's say you do because if you only call function X in ProfViz, it only profiles that function, not the 1,500 lines of code within the function, and if you're having to profile a lot of these really long lines of code, you have to wrap each of these functions all the time in ProfViz. So I don't know if you know of a better way to do it.
I'm not really understanding, because I thought you were going to say it does too much, because I found that it actually automatically does what you're saying. So there is the other side, that sometimes you're using someone else's package and it's got a lot of R code in it, and you have to sort of wade through all of that profiling that you're not interested in. So there is a way of saying profiling off, and then you do the call, and then you say profiling on again. Yeah, so that's a nice thing to know about. Yeah, as well. Yeah. Okay.
Any more questions?
Thanks for the talk. How do you go about actually profiling a Shiny app? Because it's not something that you run from start to finish. It's, you're running a couple of things simultaneously.
Yeah, it works really well on Shiny apps because you put that I've actually got an example here, but I ran out of time. But maybe since you're asking, I can show you. So it's really easy. You just, let me see if this is still working. If not, I'll explain it to you. So all you do is you just wrap that, in Shiny apps you have a call called run app or run demo. You just put that in ProfViz, then you run your Shiny app, and then you click that little red button to say stop, and then it gives you that nice flame graph for the whole thing. So it works really well. And I mean, normally, you can do your Shiny app testing in 10 to 20 seconds. So then your flame graph will run over that whole 10 to 20 seconds, or however long it takes. Yeah. Okay. Don't worry about it. No, it's fine. I think people have sat long enough. Oh, all right. So, do you want to see? All right, I'll do it quickly. So here's the example. So inside Shiny, there's various examples. So this run example is exactly like run app or something for other things. So if I just run this. So there just pops up this little Shiny app. And then I'll play around with this one little control for a while. Now I'm done. So basically what you do is you test whatever feature you think is running too slowly. Then you go back here. You just press the stop button. And then it knows that there's been a thing received. And now, so you can see now the work. So this was on the initial startup. And then as I was clicking the button, it showed us these little sparks are the work that it was doing as it was redrawing that plot. And if you've got a more complex thing, then you'll see the whole story for all the functions that called and everything. Yeah.
Okay. Any more questions?
Okay, thanks a lot.